Okay, so last time we took a look at using 3 points to come up with a even better integrating rule than we did with the trapezoid rule. And the benefit here is over a short range, if A and B are quite close together, then the curve, the blue curve, which is the actual function, is not going to look too much different than a quadratic term. Now, one downside here is that you need two pieces to finish off the Simpson's rule, where you only needed one of them for the trapezoid rule. So if we were doing the equivalent thing with 3 points on a trapezoid, you'd make two trapezoids. And here we're making only one Simpson's rule. The basic idea is to make Simpson's rule exact for any quadratic. In order to do that, there are three functions that you need to make it exact for. The constant and the linear term and the x squared term together form a basis for quadratic polynomials. You can form any polynomial you want through a linear combination of those three functions. Therefore, if you can make this method exact for those three individually, then it'll be exact also for any linear combination of those three. That's what we're thinking. Make it work perfect for the function 1. Make it work perfect for the function x. Make it work perfect for the function x squared. If it works perfect for all those, then it's going to work perfect for any linear combination, which means it'll work perfect for any quadratic. We end up getting the values 2, 0, and 2/3. That means I need to make sure that whatever linear combinations I use of the -1 point, the 0 point, the 1 point is going to produce the exact answer for the constant, the linear term, and the quadratic. So that's just linear algebra. So we just set up the matrix and we solve it, and you end up with A, B, and C. If, however, you want to revise that so that you make it arbitrary, then you're still going to get the same coefficients. You just have to multiply by h. But first we check Simpson's rule against something that's clearly not a quadratic and is quite nonlinear. And here we've got our 3 points. We're taking -1, 0, and 1 as depicted on the graph. And if you take e to the x for each of those points, you're going to get 1 over e, a 1, and an e. And now if we want to take the integral from -1 to 1, we can approximate that with Simpson's rule, or we can do it exactly. And if you plug in Simpson's rule, you come pretty close, 2.36 versus 2.35. That's really close, really. I mean, that's amazingly close because the spacing is so wide. I've used this gigantic spacing of 1, which is huge. I mean, nobody in their right mind uses spacing that big if you're doing numerical integration. But even if we did, the numbers come out really close. So Simpson's rule is just cleaning up. This now gives us a little more usable version of Simpson's rule. So we have a more flexible approach of choosing the spacing. If we do Simpson's rule compared to the exact rule, those are good all the way out to the 7th place. That's the first time you see any deviation. Now that we have Simpson's rule, there's almost no reason to ever use the trapezoid rule again. It seems to be putting the trapezoid rule out of business, with the exception that it's just a little more complicated in lining up these intervals. Normally we don't, we can't write down the exact answer, so the error has to be estimated, but we have the ability to do that as well. So let's just review then the attributes of the Simpson's rule. First of all, we now have a method to drastically knock down the error without making the step size too small. If we make the step size too small, you run the risk of arithmetic problems when you're taking differences of very similar values. So you don't want to get too small. But on the other hand, if you make it too big, then you're introducing a lot of kind of gross error by the fact that your geometry isn't working well. So this gives you a little more flexibility. You can drop h down to be something reasonable like 0.1 and get smashingly good results even on a highly nonlinear curve like the exponential. On point B, you almost always want to use evenly spaced points. There's been a lot of work over the years of people saying, hey, the accuracy gets worse as the derivative gets higher, so why don't we make the step size narrower when the derivative is large, and if the derivative is small, we'll go ahead and make the spacing bigger. As it turns out, it's too much work, too much trouble. Just leave H evenly spaced. So if you now go back to the Simpson's rule again, and we need to really finish off how to handle a whole bunch of points, realizing if you're trying to integrate from A to B of some function, if you're going to have more than 3 points to do that, then you're going to have to integrate from x0 to xn, where there might be a whole bunch of grid points in between. Okay, so we're just going to have to then apply our 3-point Simpson's rule so that it lines up across that whole grid. First of all, you're going to have to integrate across 3 points, and the easiest way to represent that is using these indices. So this is a nice way to describe 3 points when you really have a whole bunch to work with. Then you need to add up all those intervals, but you only have half as many intervals as you did with the trapezoid rule. With the trapezoid rule, we were adding from 1 to n, but since you're using 3 points at a time, there are only half as many sections for which you to do the integrations. Okay, well, what does that really mean? Well, the Simpson's rule works on 3 points no matter what you call them. So we just go ahead and apply it. We have h over 3, where h is the spacing between any two adjacent points. And so we're applying this term to this expression to any given 3-point interval. And then we just add them all up. Okay, well, maybe there's some things that we can do with that sum. We have overlapping points because of the nature of how we're butting up these 3-point intervals next to each other. The upper point on the lower interval is equal to the lower point on the upper interval, which means if I sort of mindlessly write a program to do this computation and then add up the right number, it'll work, but I am repeating function calls unnecessarily. And so I should do the same thing that we did with the trapezoid rule, where we align these functions up so that we don't do that kind of waste. So if you did this one step further, you could write an algorithm that would end up getting one function call for the first term, 4 times the second one, and 2 times the third one. Now why 2 times the third one? Well, the upper value, or this upper functional call for the very first interval is the same as the lower one on the second interval. So when I add these guys all up, there's going to be 2 of these, and then there will be 4 of the next one, and then 2 of the next one. And so this thing is going to go 4, 2, 4, 2, 4, 2, except at the ends. Just like the trapezoid rule, the lowest end and the upper end are only used once. So what I want you to do now is, for homework, go off and do the pseudocode for yourself. You won't turn that in. And see if you can turn the Simpson's rule to work between 0 and 2 pi. You'll have to continue to do the dividing h by 2 approach. Don't use redundant function calls. Okay, so when you write your pseudocode, then you can turn that into MATLAB code. You'll get 15 points to actually successfully code up the Simpson's rule in the way we just described. There's 2 ways to get the relative error. One is comparing to the truth, and the other way is to just do a relative error between the last 2 iterations, and you'll get 5 points for the total. I'm interested to know how many iterations does it take. I think you'll be surprised when you compare this to the trapezoidal rule, when you compare the Simpson's rule going to 10 to the minus 8th and the trapezoid rule going to 10 to the minus 4th.